Hello everyone, welcome to today's webinar. My name is Randy, I'm from Element 14. I'll be your host today. Today's presentation is from Texas Instruments. It's entitled More Channels and Less Space, New Trends in Highly Integrated DACs. This webinar will be presented by Kevin Duke and Sedania Abraham. Kevin is a systems engineer in the Precision Digital to Analog Converters Group at Texas Instruments, where he's responsible for industrial automation DAC product definition and development. Sedania is a product line manager in the Precision DAC group. At the end of this presentation, there will be a Q&A session. You can ask your questions in the Q&A window of the WebEx screen. So let me hand it over to Kevin and Sedania for today's presentation.
Okay. Thanks, Randy, for the introduction. And I think we'll get right into it, and we should have plenty of time left at the end for the Q&A. So basically, what we're talking about today is a combination of a individual product from Texas Instruments along with surrounding and supporting circuitry to basically construct a PLC analog output module. And we defined that product and the reference design based on real goals from actual PLC manufacturers, which are being driven by these two primary vectors of increasing the density of their modules, or if you want to look at it the other way, reducing the size of their modules, and simultaneously reducing the cost of their modules. So we need to integrate more devices and help them meet both of those goals. Along the way, though, integrating more and more stuff in these type of systems can also introduce heat. And so the hotter the module is, the more difficult it is to reduce the size. So we have two problems that we have to solve kind of at the same time. So we came up with these basic design goals, which are quite common for most PLC manufacturers, which are listed below. Hitting kind of the high points, we're going to have 4 channels with 16 bits of resolution supporting both voltage and current outputs. The voltage output in the span of plus minus 10 volts, and the current outputs kind of in the most ubiquitous terms of 4 to 20 milliamps. The magic number that we're trying to hit in terms of power dissipation, which sort of relates to heat dissipation, is less than 1 watt. For both the voltage and the current output, we'd like to achieve less than 0.1% full-scale range max total unadjusted error. That's the error prior to any calibration. And you'll notice maybe some clues into how we're going to achieve this by the notation of peak-to-peak ripple goals for the current output and the voltage output. Because we're going to have to utilize a switch mode power supply in order to realize the efficiency we need to hit less than 1 watt of power. Certainly couldn't do that with an LDO. And at the same time, we have to be mindful that manufacturers or designers in this particular space have to go against pretty stringent immunity standards represented by the IEC 61000-4 immunity goals, which is ESD, EFT, or electrically fast transient, conducted immunity, radiated immunity, and surge. Moreover, the results from IEC 61000-4 are graded in classes, and basically we certainly don't want to see Class C or Class D results. We'll accept Class B, but really we're targeting Class A. And Class A performance gets to be defined by the manufacturer or designer. So in this case, since we're setting total unadjusted error goals of 0.1% full-scale range, we'll go ahead and define Class A as the same as 0.1% FSR. Pardon me. So this slide shows pretty conventional circuitry utilized in order to realize both current and voltage output for these systems. So for the current output side, which you see on the top of the circuit, we have this so-called two-stage high-side voltage to current converter. And items of particular merit for the current output is that typically the max impedance we see someone needing to drive is about 1 kiloohm. However, for current output, it's a perfectly valid load condition to drive 0 ohms or 1 ohm, something very, very small. In addition, we typically see this kind of 12 to 36 volt high side supply voltage in this particular case. I mentioned 12 to 40 volts because that's what ended up being realized by this design. So we actually have 4 volts of headroom on the high side. And we'll get a little bit more into the implications of this particular structure for a high side current source. But it's quite typical for current outputs in these systems to be in a high side configuration. Meanwhile, for the bottom half of the circuit, we have just a kind of simple gain stage, because typically the DACs that are available are SPI interfaced and relatively low voltage devices operating off of maybe 5.5 or so volts with output spans from 0 to 2.5 or 0 to 5 volts. For industrial, we want to see kind of at most plus minus 12 volts. So we need a kind of simple gain stage in order to realize those output spans. The minimum impedance for the voltage output is about 1 kiloohm and upward. You typically don't see anything less than 1 kiloohm for the voltage output. So zooming in a little bit onto the current output, or the top half of the previous slide, I mentioned this potential case of driving a very, very small load. So in this particular example, we're looking at a 1 ohm load. The design we are discussing did kind of the most ubiquitous current output, like I said, of 4 to 20 milliamps, but quite often there are other variants as high as 24 milliamps. So we're kind of looking at the worst case on the left side with a 1 ohm load and 24 milliamps of full-scale current into that load. Again, typically AVDD goes from 12 volts to 36 volts, but nominally 24 volts, and basically you get plus minus 50% tolerance on that supply voltage. So a nominal case in terms of supply, pretty bad case in terms of output current and output load. In such a case, you can imagine that most of the voltage or most of the power is dropped across the sense resistor and this PMOS. And in reality, the sense resistor is quite small for these kind of circuits. So most of the power is dissipated across this PMOS. And so the thermal camera image that you see is an integrated circuit that integrates the DAC reference and other associated circuits, as well as this two-stage high-side voltage to current converter circuit. And what you're seeing then is the heat as a result of all of this voltage or all of this power being dissipated across the PMOS instead of across the load. Altogether, basically, we're consuming nearly 600 milliwatts of power, and from ambient, the integrated circuit is heating up to nearly 60 degrees C. The concept behind this quad channel design basically was then to implement a feedback loop along with a buck boost converter that modifies the high side supply voltage that are sent in the PMOS-C. So in this particular example, again with the 1 ohm load and 24 milliamps, instead of RSense and PMOS seeing a 24 volt high side supply voltage, they see something closer to 4.5 or 4.7 volts. As a result, then the power dissipation is reduced quite significantly to 185 milliwatts, and the temperature is closer to 37 degrees C. So we've achieved 2 of our primary goals in terms of enabling this smaller design form factor and increased density by reducing power dissipation and by reducing the heat that's dissipated from the device. So the device that is behind most of this is what we call the DAC 8775. It's a 16-bit DAC, actually 4 channels of 16-bit DACs, each with voltage or current outputs, and the feature that we've dubbed adaptive power management, basically the capability of moving that high side supply voltage in order to maintain the best power dissipation irrespective of load. So if we're driving a 0 ohm load, if we're driving a 1 kilo ohm load, we're always at the most efficient operating corner. So basically, we implement most of the conventional current output spans and voltage output spans, which are selectable via software, so you don't have to change resistors or anything of that nature. So 0 to 20 milliamps, 4 to 20 milliamps, this 3.5 to 23.5 milliamp span, which maybe looks a little bit odd, but this was designed to accommodate for the so-called NAMR specifications, which allow for basically 4 to 20 milliamps as signaling, but then overcurrent and undercurrent conditions to indicate alarms. 0 to 24 milliamps, the kind of widest unipolar span, along with plus minus 24 milliamps, which is kind of a unique case, but there do exist some PLC modules. Most commonly, we hear the story about bidirectional valves that need to turn both ways, and they're implemented using a bidirectional current source. For the voltage outputs, 0 to 5 volts, 0 to 10 volts, plus minus 5 volts, and plus minus 10 volts, along with 20% overrange for each of those 4 output spans, so a maximum of plus minus 12 volts. Speaking on a high level, we're saying the TUE is about 0.1% full scale range max. If you open the data sheet, the TUE is kind of broken out for each of the previously mentioned output spans, as well as with respect to operating temperature spans. We provide specs at room temp, so you have some idea of what your calibration scheme would have to look like, perhaps, along with specs that go from kind of conventional industrial operating temperature from minus 40 to 85 degrees C, and with what we call the extended industrial operating temperature range, which this device supports, from minus 40 to 125 degrees C. So looks like, at least on the high level, that DAC 8775 is going to be a good part for this reference design. I mentioned the adaptive power management feature within the context of a current output, but the actual structure implemented is what we call single inductor multiple output buck boost converter, which, as you can see on the graphic on the bottom right, we have just one inductor along with 2 diodes implemented as kind of the 3rd and 4th switches for the structure, which allow us to generate both a positive and negative supply voltage. So for the current outputs, we're going to move around this high side supply voltage, or perhaps a negative side supply voltage in the case of plus minus 24 milliamps. But for the voltage outputs, we can simultaneously generate a positive and negative 15 volt supply, for example, to support the plus minus 12 volt output span. So basically then, with this capability of the SIMO DC-DC coupled with an internal 5 volt LDO for the digital supply, suppose you're implementing digital isolation, you need a supply voltage for the hot side of the isolation scheme. We can provide that from our device, and 5 volts, 10 ppm per degree C reference. So basically then, from a single input supply, we can generate plus minus 5 volts, a 5 volt digital LDO, and a 5 volt reference, which is everything that our device and kind of the hot side of the system needs in order to be operational. So from a single supply from 12 to 36 volts, we do everything else, which is quite convenient when we're talking about the topic of reducing size, because now you don't have to generate 4 total supply rails in order to support the system. Again, kind of on the topic of stringent safety standards for industrial, I mentioned this IEC standard, but there's also a need for redundancy in terms of intrinsic safety or ATEX or SIL ratings, and therefore we implemented some kind of enhanced reliability features. Kind of on the middle of the graphic on the bottom right, you can see the alarm pin, which can be used as an interrupt from the MCU to read these conditions. But we have an alarm basically then for an open circuit condition on the current output, a short circuit condition on the voltage output, a thermal alarm, which would indicate that the die has reached kind of an unsafe internal temperature, compliance voltage for the current output, and then also a watchdog timer and a CRC feature for the SPI interface to make sure you're always doing what you intended to do from the microcontroller side. In addition to those features, the device is kind of smart, if you will, and can be programmed to automatically go into kind of a fail-safe state if one of these conditions are reached. And by fail-safe, we kind of mean you could switch off the DC-DC converters and power off the current output such that you're in kind of a zero output state and there are no high voltages present from the DC-DC as well. Altogether, this guy goes into a 10 by 10 millimeter QFN, which again is kind of helping us realize our size goals. So the two graphics here are intended to kind of give an idea of what the efficiency of the DAC 8775 looks like. And since we have a number of variables here, we kind of represent it in two graphs because we operate from an input supply from 12 to 36 volts, which definitely impacts efficiency. And then depending on what the load is, this high side supply voltage also changes, and this modifies our power dissipation. So at a first level, on the left side, you can kind of see this topmost blue curve, which represents a 12-volt PVDD. Looks pretty nice from an efficiency standpoint. It gets to above 80% efficiency for all output currents above 10 milliamps or so. And it looks okay for currents below 10 milliamps. On the other side of the slide, you see power dissipation versus supply voltage for different load conditions. So basically, at the 12-volt mark on the x-axis, you can see power dissipation for loads from 1 ohm up to 1 kilo ohm, which is kind of the conventional span that we're targeting for these PLC analog output modules. And the kind of figure of merit finally there is that you can see that we're below this 1 watt target for power dissipation. And this is power dissipation on our board, of course, not counting the power dissipation across the 1 kilo load. In the end, it's about 750 or 780 milliwatts, but only when operating from a 12-volt supply voltage. And as I mentioned before, we could see 12 to 36 or potentially even 40-volt input supply voltages. So while it's well and good that the DAC 8775 is very efficient and quite well below 1 watt at 12 volts, we have to find some method of modifying this input supply voltage down to 12 volts in a very efficient way. And this is basically where these pair of TI designs come in. So utilizing the buck converter called the LM5166, which is a high efficiency light load, relatively speaking, buck converter, we can take a 12 to 40 volt input field supply and buck it down with about 93 to 95% efficiency to a 12 volt supply where the DAC 8775 is most efficient. So altogether, the intention then is that the combined power dissipation of the DAC 8775 and the LM5166 will be beneath 1 watt of power dissipation. You'll also notice this kind of note that says up to 65 volts. The LM5166 can actually support a supply voltage up to 65 volts, but at such high voltages, the efficiency is going to change and probably not be beneath 1 watt of total power dissipation. We separated the two topics into two reference designs, TIPD215 focusing on power and efficiency, and TIPD216 focusing on the IEC 61000-4 compliance aspect. You can see a small graphic on the bottom of the slide, one depicting kind of a block diagram, and the other depicting a 3D rendering of the PC board layout and illustrating the solution size. So I'm making some assumptions as to the robust needs of the IEC 61000-4 protection block, but altogether the protection circuit the supporting DC-DC components and the DAC itself consume about 68 by 58 millimeters, which is about the size maybe of 2/3 of a cigarette pack or maybe a big business card. Just zooming in a little bit more on the left side, you can see kind of a zoomed in picture of the block diagram with more details. The previous slide was maybe hard to see. And on the right side, the physical PCB, a photo of the board that we built and tested. Kind of the important thing to note about these TI designs, maybe in the past with reference design collateral, it's hard to tell, was this an idea somebody had and drew up on the back of a napkin or a pizza box and thought it was a good idea, but they never simulated it or tested it. Or maybe it was just simulation, or was it actually built? This was, by definition, calculated, simulated, and built and measured. So it's actual real-world results that were really actually tested. So the primary goal that we wanted to hit was this power dissipation, and again, this is the cumulative effect of the DAC 8775 along with the LM5166. Across 10 PC boards, what's plotted here is the worst case for each of these loading conditions. So the worst case ends up being this 1 kilo ohm load condition, followed very closely by the 0 ohm load condition. But you can see that for all cases, the design is below our targeted 1 watt power dissipation goal. Going on to the other goals, we did actually hit our accuracy goals quite well for the voltage output, and you had another 10 millipercent of buffer for the current output. Hit the power dissipation goals. Of course, the device kind of intrinsically met our resolution and output span requirements. The ripple was just marginally higher on the current output than we had set out to meet, and quite well bounded for the voltage output. For the IEC 61000-4 immunity tests, we had Class A results in everything except for radiated immunity and conducted immunity, which we achieved Class B results. For conducted immunity, not necessarily surprised to see Class B results. It's actually quite common because the band of interest for conducted immunity goes down to bandwidth that is quite common for precision instrumentation to be able to react to. Meanwhile, for RI, this starts at very, very high frequencies. So I'm a little surprised to see Class B for RI, and to be honest, I think that was the artifact of the test setup. We were attempting 30 volts per meter conducted radiated immunity testing, and the test standard itself actually describes that the antenna needs to be about 1 meter away from the device under test or equipment under test. But in order to hit 30 volts per meter, which is actually quite intense, enough to cook some popcorn perhaps, the antenna was placed basically directly on the board. And I think that created some artifacts, as I've never seen Class B radiated immunity tests for a precision device like this. But on the whole, we did manage to hit all of the intended results. So with that, we can kind of open it up to questions now. I've also put my email address on the slide. If you're not so inclined to ask a question vocally, you could feel free to email me.
Well, we have 3 questions already. Let's start with the first one. Can this device detect when the load has changed or detect if a coil winding has failed?
I'm trying to look at the chat. So basically, the load question is quite relevant. So the idea of the adaptive power, there's three operating modes for the DC-DC. The first one we call full tracking, the second we call clamp mode, and the third we call auto-learn mode. So full tracking mode would completely react to any change in the desired output current, as well as any change in the load impedance. So barring some kind of compliance voltage condition, if you were to try to drive a load that's too big or drive too much current into a large load, you'll always see the desired output current across the load. Clamp mode kind of changes the operating corner a little bit, basically by reducing the minimum voltage that the DC-DC would output. So suppose you're kind of using this device with known loads and known maximum output currents, and you don't want to deal with full tracking mode. You would just set this clamp voltage and it would maybe never change. The reason somebody might do such a thing is because the output signal chain itself, we're talking about settling times on the order of microseconds. But for a DC-DC to slew, typically we're looking at something more on the order of milliseconds. So if you want to maybe compromise between power dissipation and slew rate, it would be in your best interest then to have the DC-DC set at a static voltage so that you don't have to wait for the DC-DC to slew, and you just get this microsecond slew rate associated with the signal chain. Auto-learn mode is a little bit different, where basically if you didn't know the load but you kind of wanted to operate in clamp mode, the device automatically detects what the load impedance is and then automatically sets the clamp voltage to an appropriate voltage to drive that load. So three kind of different operating conditions depending on what your priorities are and the trade-offs between efficiency and slew rate or settling time. The coil question, I don't totally understand. There's any more details, but off the top of my head, I don't know how to answer that one.
The next question is, how fast can the DAC be changed over its full range of 16 bits?
So that kind of relates to the previous point as well. It depends if you were talking about something in full tracking mode or in one of the clamped modes. I think if you were to go from the full-scale range of plus minus 24 milliamps for the current output, this is the worst case. It takes about 2 microseconds to slew from minus 24 to plus 24. If you were doing one of the unipolar ranges, something closer to 1 microsecond, which is also true for the voltage output. But if we're talking about something with the DC-DC active, and again, in the case of plus minus 24 milliamps, it's closer to 2 milliseconds to slew from negative full scale to positive full scale. Full tracking doesn't apply for the voltage output, so it would always be 1 microsecond.
How sensitive are the detection circuits for voltage and current changes?
I'm not totally sure what that's directed towards. Changes like compliance voltage, or I mean, we're going to, in a typical operating condition, we are controlling the voltage and current outputs with resolution of 16 bits, depending on the output span. The exact, granularity of that changes, but otherwise I don't really understand the question.
The next question is kind of a follow-up for the first one. The coil winding question was considering this device driving an inductive load such as a motor or transformer. I wonder if a coil burnout could be detected and the power cut off before catastrophic effects set in.
Yeah, I mean, the only way that we might be able to detect some kind of coil burnout, again, all we're trying to do is measure the effective current that we're delivering to the load. So if it became an open circuit condition, we could detect it. If we hit compliance conditions, we could detect it. But otherwise, it would, I guess, depend on exactly the nature of the inductive load failure for us to have the capability of actually reporting the failure.
Next question. You can drive the DAC at 16 bits, but can you monitor the changes in the load at the same resolution?
Like the capability of reporting the load impedance at 16 bits, I suppose. In the end, we're not really providing much of any information on what the load is. Again, really the principal purpose is to drive current or voltage into a load. I guess if you were, you could maybe try to use clamp mode and the current output readback to detect what kind of load you're driving along with the compliance voltage alarm, but it would definitely not be 16 bits of resolution to detect load impedance.
Are there any more questions? There appears to be no more, so that concludes today's webinar. I'd like to thank Kevin for delivering an excellent presentation, and I'd also like to thank everyone who has taken the time out of their busy day to attend.